Welcome back. In this and the next couple of videos, we're going to talk about the chi-square test, which is a test that you can use to evaluate categorical variables in your data if the target is also categorical. That is, if your target is binary or multi-class. Or in other words, if you're working in a classification scenario. Chi-square is a statistic metric or a statistical test used to determine if two samples of categorical features were extracted from the same population. And what the chi-square test does is it compares the distributions of the categories extracted from the different samples. The chi-square test has two main uses. One is to assess the goodness of fit, and the second one is to test the independence of two variables. When we want to assess the goodness of fit, we want to assess if a certain feature follows a hypothesized distribution. When we use it as a test of independence, we want to compare or determine if two variables are associated. For example, if the variable gender, thinking of the Titanic dataset, is associated with survival, which is the target. So to select features, we're interested in using chi-square test as a test of independence because we want to see if the categories in the features are associated with the outcome. But I'm going to start explaining how we use chi-square for the goodness of fit because I think it's easier to understand what this test is doing. So using chi-square to assess the goodness of fit is to determine if a categorical variable follows a hypothesized distribution. For example, I'm thinking again in the Titanic dataset where I have females and males and I want to determine if they survived. If gender had absolutely no effect on survival, and say I have a dataset with 200 women and 100 men, I would expect that half of the women survived and half of the men survived. So this distribution that I'm showing in this slide is the expected or hypothesized distribution. This is what I think should have happened given my hypothesis. Now we can also show this as a contingency table, and I'm going to do that later on. But at the moment I show the expanded table because it's easier to understand what's coming up. So if I take a random sample from my distribution of male and women in the Titanic, I'm going to obtain a certain percentage of women who died, survived, and male that died and survived. And then what I'm going to do is I'm going to compare the frequencies in my extracted sample with my expected distribution. It's fairly obvious that random samples are random, so the distributions are not always going to be identical to the expected distribution. There is going to be some variability. For example, here I take another sample and I see that I have 95 women that died, 105 that survived, 45 men that survived, and 55 that died. Now, is this distribution similar than the expected one? The chi-square test will help us determine so. Now, if we continue extracting more random samples, we're going to obtain a different distribution of male and female in the categories survived and not survived. So with the chi-square, we can obtain a value that tells me if the distributions that I took out from my hypothetical distribution come indeed from that distribution or not. Now, the good thing is that this chi-square statistic follows the chi-square distribution. And this distribution has been long studied and very well characterized, so we don't really have to invent the wheel. We just need to take the values from the previous slide and enter them into the chi-square distribution that I show, for example, here in this slide. And just to clarify, in the x-axis we have the values of the chi-square statistic, the ones that I showed you in the previous slide, and on the y-axis we have the probability of, given this chi-square value, that the sample we took belongs to the hypothesized distribution. And the chi-square distribution has one parameter, which is the degrees of freedom, and I'm going to come to that parameter a bit later in this video. But our distribution has only 1 degree of freedom, so with this chi-square distribution, I can then go ahead and look for the values of chi-square that I obtained previously. For example, the value 1.5 falls in this line, and this means that it has this probability of belonging to the hypothesized distribution, so the probability is quite high, so most likely I took that sample from my hypothetical distribution. But the other chi-square value, for example 15, is actually quite unlikely. So what this means is that the random sample that I took, the one that is number 3 in my slide, is very unlikely that belongs to the hypothesized distribution. Now, there are 2 scenarios here. One is that I really took the sample from my hypothesized distribution, and there is a small, tiny chance that that distribution does belong indeed to the hypothesized distribution, because you can see that the probability is not 0. But if I was trying to determine, like if I didn't know where I took my sample from, and if I want to determine does it belong to my hypothesized distribution, well, the probability is so low that I most likely say, no, it doesn't. It has a different distribution. So how is this chi-square statistic calculated? It's a very simple statistic. It just evaluates the observed value versus the expected value. So for this random sample 3, the observed value for female that died is 120, and the expected value is 100. So I subtract one from the other, I squared so that I work only with positive values, and then I divide by 100, which is the expected distribution. I move on to the next cell, and then the observed females that survived are 90, the expected were 100, take the difference, I squared, and I divide by the expected distribution, and I do the same with the male that survived and the male that died. When we perform these computations, here we obtain the values for each one of the cells, and then we get the statistic that in this case is 15. With this value, we can go again to this distribution and assess the probability of random sample 3 being the same as the theoretical or expected distribution. Now, here I am assessing 2 variables. One is the variable gender versus the other categorical variable that is died or survived. So instead of showing these values of frequencies as an extended or unpacked table, we can better represent this information with a contingency table where we have one variable in the columns and the other variables as the rows. So here we see the observed distributions that I extracted in my random sample number 3, and on the right we see the expected distributions. Now, this is fantastic when we actually know what we expect. But for your datasets, most likely you don't know the expected distribution. For example, let's say I want to assess if being a cat or being a dog affects the color of the fur of the animal. I don't really know the expected probability of this. I mean, you could know it if you were an animal expert, but indulge me, we don't know it. Fortunately, there is a way of calculating the expected probability. And to calculate the expected probability, we first need to obtain the marginals, and the marginals are the total number of cats, the total number of dogs, the total number of animals with brown fur, and the total number of animals with ginger fur, and of course the total number of observations. So the expected probability can be obtained by multiplying the marginals and then dividing by the total number of observations. So for the first cell, we multiply the marginals of the total number of brown animals times the total number of cats, and we divide by the total number of observations. Then for the second cell, we take the total number of brown animals, we multiply by the total number of dogs, and then we divide by the total number of observations, and so on. With this, we can obtain the values of the expected probabilities. Now, if you're wondering why we multiply the marginals and divide by the number of observations to obtain the expected distribution, this comes from theory of joint probability. So later on in the course, I will add a video that is optional in case you want to know more about this. But for now, I'm going to assume that you believe me that this is the correct way of calculating the expected probabilities. So now that we have the expected probabilities, we are in a good place to repeat the exercise that we did before, where we're going to take the observed value, subtract the expected value, square the difference, and divide by the expected value. So for cats, it's going to be 200 minus 210.8 square divided 210. For brown dogs, it's going to be 60 minus 49.19 divided 49.19, and so on. Now, for the sake of completeness, these are the results of these small calculations, and if we add all these values up, we're going to obtain a statistic, the chi-square value, that is 9.84. And if we go with this value to our curve, we're going to see that the probability of cats and dogs having the same distribution of brown and ginger fur is very low. So we're going to conclude that there is an association between the color of the fur and the animal, because cats and dogs do not have the same distribution. Now, something that I want to clarify is that when we say that cats and dogs don't have the same distribution, it doesn't really mean that we have to have 50% of cats that are brown and 50% that are ginger. We can as well have 20% of cats that are brown and 80% that are ginger, but if there was no association between animal and fur, I also expect 20% of dogs to have brown fur and 80% to have ginger fur. Because we rejected this hypothesis, it means that the distribution of fur depends on the species of the animal. So now, I mentioned previously that the parameter from the chi-square distribution is the degrees of freedom. So how do we calculate the degrees of freedom? It's very easy. The degrees of freedom for any contingency table is the number of rows minus 1 times the number of columns minus 1. So in all the examples that we were working with in this video, we have 2 minus 1 times 2 minus 1. This means that the degrees of freedom for our distributions is 1. So I hope I gave you a good intuition of what the chi-square test is doing and how we calculate it. So when can we use it? We can apply this test only on categorical variables when the target is either binary or multi-class. So it's not suitable for regression, it's not suitable for continuous variables, at least out of the box. You could use it on discrete variables as well, if the number of unique values are not too high. And it is used to assess the association between the categorical variable and the target. So if the p-value is very small, it means that there is an association between the categorical variables and the target, because we don't have the same distribution over the different categories when the target is 1 and when the target is 0. So how do we use the chi-square to select features? Very easily. We take our categorical variable, we take our target, and we build a contingency table. If we have more categories and the target is multi-class, we're going to have bigger contingency tables, but the procedure is identical. We calculate the expected distributions with the marginals, and then we subtract the observed from the expected, squared, divide by the expected, add all up, and we obtain the chi-square value. With that, go to the chi-square distribution and obtain the p-value. Now this sounds like a lot of work, but you can actually do it in 2 lines of code thanks to scipystats. In fact, scipystats has a function that is called chi-square contingency that does all of the steps that we mentioned in the previous slide automatically. So after we obtained the p-values for each one of my categorical variables, we need to do this for every categorical variable, we rank the features based on the p-value or the chi-square value doesn't matter, it's the same. The thing to keep in mind is that the higher the chi-square value or the lower the p-value, the more predictive the feature is. In other words, the higher the association of the categories of the feature with the classes of the target. And once we ranked all these features, we then select the top ranking features. Now here comes the arbitrary point, which is where do we put the cutoff? This is up to you. We can select the top 10 features, the top 10 percentile, all the ones that have chi-square values bigger than the mean of the chi-square value of all the features. I mean, there is a lot of room to decide. We can also select it based on the p-value, and I'm going to discuss how to select features based on p-values at the end of this section. For the time being, in the next video, we're going to see how to rank features using the chi-square in Python, and then I'm going to talk about the considerations that we need to think about when we use chi-square to select features, and later on I'm going to give you an intuition on why we use the marginal probabilities to calculate the expected frequency. With this, let's move on to the demo.